Nascent Atomic Theory. A short essay by Bruce Mills, otherwise known as The Obligate Pedestrian. Because the first part of this essay has the feel of a manifesto, I would like to start by saying that I have no hidden agenda. I believe that modern mathematics, chemistry and physics are all very good theories, the likes of which have never been seen before on this earth. I do not believe that they are the last word, but I also do not believe that, say, the 12th century alchemists had access to some arcane knowledge well in advance, but which is lost or kept hidden by adepts who are not letting the common folk get hold of it. These essays are ultimately my way of talking about orthodox science through the ages. The only idiosyncrasy is that I deplore calling anyone idiots in the modern sense, but I'm happy to call them idiots in the original sense of being their own person and perhaps ignorant of those things that the future will bring. But aren't we all? I try to understand what it is that each person really believes and why. The conceit, in a literary sense, of the skeptical alchemist behind this series of essays is to look at modern chemistry from the point of view of an alchemist who is skeptical that modern chemistry is anything other than modern alchemy. If not for a linguistic foible, we would today be talking about the latest work in quantum alchemy and the theory of quantum essences. This specific essay looks at atoms from Empedocles to Dirac, which in some ways is a full circle. In the view of several significant historians and practitioners of science, the atomic theory is close to the most important and significant idea in science. I do not share this view. This is mainly because there is not really any such thing as the atomic theory. Right from the start, there have been corpuscular theories and fluid theories and elements and principles, but these things are just vague and obvious ideas looking for a home. Feynman in the 1960s answered the question, if one had to restart science from just one idea, what should it be? By saying that the idea should be that all matter is made of small particles. I think that this idea comes naturally to humans and does not have to be stated, but also that this idea is not entirely correct and has always been one of several ideas that led eventually to quantum mechanics. The alternatives are usually forms of fluid or field theory or a smooth particle concept going back to ancient or medieval times. But the lumpiness or clumpiness is an idea that occurred to multiple people through history of the development of chem, alchemy, chemistry and chemistry. The first truly new thought was electromagnetics by Faraday and Maxwell and others in the first part of the 19th century. This matured into quantum theory by Planck, Einstein, Heisenberg, Schrödinger and Dirac and others in the first part of the 20th century. It opened a path to a strongly different and more successful science of materials, and that science was not about particulate atoms but about fields and fluxes, much more similar to alchemical principles than to chemical atoms, and it depended strongly on hundreds of years of mathematical development. Modern atoms are particles in name only. The curious point here is that until 1905, when Einstein wrote a paper that deduced the size of atoms from microscopic observation of the motion of pollen grains, the atomic hypothesis was considered by most to be a mathematical trick to allow combinatorial conclusions about reactions, and the atoms of the chemists, the crystallographers and the physicists were all different kinds of things and rather incompatible. This was fine since most people held their ontological status to be questionable. But by 1930, a fairly well-formed atomic theory had been created with the idea that atoms are not hard, indivisible lumps at all, but rather more like ocean waves, a storm in an extremely small teacup. The substrate of chemistry is quantum fields, not classical particles. So the atomic theory in terms of little hard particles that bash into each other was essentially only ever an approximation and an ill-formed and contradictory idea that was considered to be demonstrated and accepted for only about 30 years in the 3,000 years of history of the science of materials. This essay, however, is a brief survey of some of the ideas of atomic theory, focusing mainly on the period in Europe around the year 1700, plus or minus a few decades. In 1704, John Freind, MD, student of Christ Church and Professor of Chemistry, read a lecture at the Oxford Museum titled Chemical Lectures in which almost all the operations of chemistry are reduced to their true principle and the laws of nature. This could be taken as an implicit definition of chemistry as being based on the explicit modelling of atoms in an atomic theory. Of course, multiple researchers defined alchemy, chemistry and chemistry in different ways. But coming up to the 1730s, some form of stable distinction is forming, with alchemy and chemistry getting the boot. Given that Freind, officially a chemist, is giving a description of the rules of chemistry reduced to their true principles and laws of nature, he appears to agree with the basic phenomenological conclusions of those he calls chemists, but feels that they have the causes wrong. My position on this is that cause is an ill-formed concept that in no manner can ever be measured. There are, it is true, robust correlations between measurements, and those are very useful to know, but they are not causes. Never can we demonstrate actual causes. Cause is a way that humans like to organise correlations and controls. In the first lecture of the Principles and Operations of Chemistry, Freind lists axioms of atomic theory, which I paraphrase here. 1. For each shape, volume is proportional to the cube of length. 2. Momentum is the product of mass and velocity. 3a. A body that is more dense than ambient fluid sinks. 3b. A body that is less dense than ambient fluid rises. 4. All parts of matter are drawn to each other. 5. The attraction between atoms is inverse square or more. 6. Attraction between atoms varies with the material. 7. The attractive forces can vary with direction. 8. I'm going to skip this one for now. 9a. Particles can adhere to each other. 9b. The force with which atoms adhere can vary with the nature of the contact. The actual phrasing is somewhat opaque to the modern ear. For an example, consider a more direct translation from the Latin, by an unknown translator, of the first proposition. All similar bodies are in triplicate ratio of their homologous sides, and therefore spheres are in triplicate ratio of their diameters, or are as the cubes of their diameters. Also, in similar bodies that are of the same density, their weights are as the cubes of their diameters, but their superficies are in a duplicate ratio of their diameters, or as the square of their diameters. End of quote. Triplicate ratio means proportional to the cube, and homologous sides means one compares the corresponding sides. For example, one compares the edge of the square to the edge of the square and not to the diagonal. The last part says that areas are proportional to the square of lengths. Superficies would be surfaces, that which is superficial in the more literal sense of the word than is usual in the 21st century. Proposition 1 is geometry. Proposition 2 defines the moments of bodies or the quantity of motion, which I have phrased here as the latter term, momentum. It actually says the moments of bodies or the quantities of motion are in ratio compounded of the quantity of matter and their celerity. Celerity is swiftness of motion and can just be taken to mean velocity. It is also another word for proper velocity in relativity. The quantity of matter means more or less mass, so this states that the quantity of motion is the quantity of matter times the velocity, or at least proportional to this. Proposition 3 is buoyancy. Propositions 4, 5, 6, 7 is a description of the force between atoms, although it's mainly about keeping the options open. The force might vary with distance and direction, and there might be an extra contact force, which might also vary with direction. Proposition 8 seems to be an attempt at dynamics, how atoms move in response to the forces. There seems to be very little note of acceleration, and so the physics is more that of there being a force that causes a velocity rather than the Newtonian force. This feels somewhat Aristotelian, which is odd given that Freind writes about Newton's Principia and explicitly mentions Newton as an influence. So while Freind admires Newton's methodology, he seems to be of the opinion that the actual rules for atoms are different than for planets. Very different. Arguably, he was right. Proposition 8 is specifically particles. By how much more minuter they are, with so much the greater velocity they approach each other. For the attractive force exerts itself only in those particles which are very near one another, as for instance in D and C. The force of such as are remote is next to nothing. Therefore, no greater force is required to move the bodies A and B than what would put into motion the particles D and C when disengaged from the rest. but the velocities of bodies moving the same force are reciprocally as the bodies themselves. Therefore, the more the body A exceeds the particle d in magnitude, the less is its velocity, and this motion is so languid that oftentimes it is overcome by circumambient medium and other bodies. Hence it is that this attractive force does scarce exert itself unless in the smaller particles separated from the rest." End of quote. The diagram accompanying this seems to be of two spherical bodies named capital A and capital B, with points on their surface named lower C and lower D. The 2 points are very close to each other and seem to be the cause of attraction between the two spherical bodies. However, another interpretation is that this is supposed to show two large bodies attracting each other and two small bodies at the same surface-to-surface separation also attracting each other. This proposition feels like postulate 5 from Euclidean geometry. It feels like the writer has something in mind that they are unsure of and have added in a complicated explanation, hoping it will stand for an axiom. What does proposition 8 mean? Proposition 8 seems to be an attempt to discuss the dynamics of the particles, how they move as a result of being near or far from each other. I will separate this into clauses. Clause 8.1. Particles by how much minuter they are, with so much the greater velocity they approach each other. This is asserting that smaller particles attract each other more, or at least move faster, that is, respond more to the same force. I think he means to imply smaller particles of the same mass and same surface-to-surface separation. Before the next clause there is a diagram which I think is intended to mean to compare two particles A and B of low density and two particles C and D of high density, but separated by the same amount. Clause 8.2. For the attractive force exerts itself only in those particles which are very near one another, as for instance in D and C. Clause 8.3. The force of such as are remote is next to nothing. Clause 8.4. Therefore, no greater force is required to move the bodies A and B than what would put into motion the particles D and C when disengaged from the rest. Smaller particles move faster as they approach each other. The praise that Freind gives to Newton resonates oddly with the Aristotelian physics that is used in the definition of the atoms. Further, Freind suffers from exactly the same deficiency he accuses the Cartesians of. I feel that I need to quote at length from the Chemical Lectures, page 175. It has been the constant method of the Cartesians and of those too, for the most part, who call themselves mechanical philosophers, to assume an hypothesis or figment which has no foundation anywhere but in the imagination only, and then in general terms to tell us how everything in nature may be produced according to that hypothesis without being able to give a clear and satisfactory account of one single appearance." End of quote. Here Freind declares that the Cartesians and also the mechanical philosophers make up random hypotheses according to their personal imaginations. This feels like a misreading of the intention of the discourse of Descartes on the method for rightly directing one's reason. Descartes wanted science to work like Euclidean geometry, reason from self-evident principles. But ultimately, self-evident actually comes from observation. You cannot declare principles to be self-evident if you have never actually seen the topic of the discussion. Further, Freind then declares that the Cartesians and mechanical philosophers in practice fail to produce any workable theories. Start of quote. Nothing of this kind can be charged upon Sir I. Newton. He assumes nothing but observation and experiment, which are evident to the senses of all mankind, and from thence he deduces demonstrative conclusions, and then again by assistance of these conclusions he explains the causes of many phenomena in nature. Thus it is evident by undoubted observation that the planets move in ellipses round the Sun and describe areas always proportional to the times, and that the satellites do the same in respect to their primary planets. End of quote. Here Freind gives Newton too much credit. Firstly, the observations of the positions of dots of light in the sky, dots that move around and oscillate backward and forward at times. Kepler did a lot of work on this data to establish that from the point of view of the Sun, these orbits were ellipses. it being not at all obvious from the observations alone. The three laws of planetary motion of Kepler are not observations but approximate summaries of the data available. We know that they are not exactly correct. Newton then worked from the deductions of Kepler about the approximate behaviour, which was then presented as a practical rule. But the idea that the inverse square law is the cause of the motion is a vague philosophical notion rather than something that is a foregone conclusion or observation. The logic and philosophy of cause and effect is quite complicated. Start of quote. From this, he clearly demonstrates that all the planets have a tendency towards the Sun and the satellites towards the planets which they attend, that this tendency decreases in a duplicate proportion of their distance, that moreover there is a universal tendency of matter to matter, and that the tendency of the Moon towards the Earth is the very same with the force of gravity and is the cause of the flux and reflux of the sea. This tendency, or attraction, some indeed may, if they please, term an occult quality, and I believe it will always remain so, for I cannot find that the greatest philosopher among the editors will undertake to show how it may be produced mechanically. But then, however occult it be, as to its cause it cannot be called what their principles are owned to be, an hypothesis or figment, since the existence of it is as undeniably proved as that of the sun or the planets. If then there be such a principle, which demonstrably belongs to matter, what reason can there be why we may not make use of it in philosophy, and show how it is the real and adequate cause of a great many effects which we daily observe? End of quote. Freind concludes that the laws of planetary motion of Newton are deductively proved from conclusions that are self-evident once the observations have been made. This was essentially the method of the Cartesians and the mechanical philosophers. The awkward thing about all this is the axioms of atomic theory of Freind do not really follow the idea that Freind claims to adhere to. The existence of small particles of matter is not an observation, it is an hypothesis or figment. The description of the force is a combination or failure to say anything with a collection of other figments. Much of the work of Freind says that there is some kind of occult force of attraction at the distance between particles that may vary with distance and direction, and the nature of the contact force may vary with direction and the nature of the contact. Other than suggesting that there are particles and the force between particles drops to a practical zero at macroscopic distances, there seems to be not much being said, and for the most part the physics is Aristotelian, not Newtonian. Despite the problems, the propositions of Freind seem to be in some ways an improvement over those of Robert Boyle, which should be repeated here for comparison, from the Skeptical Chymist. Proposition 1, page 37. It seems not absurd to conceive that at the first production of mixed bodies, the universal matter whereof they among other parts of the universe consisted, was actually divided into little particles of several sizes and shapes variously moved. Proposition 2, page 38. Neither is it impossible that of these minute particles, diverse of the smallest and neighbouring ones were here and there associated into minute masses or clusters, and did by their coalitions constitute great store of such little primary concretions or masses as were not easily dissimible into such particles as composed them. Proposition 3, page 45. I shall not peremptorily deny that from most of such mixed bodies as partake either of animal or vegetable nature, there may, by the help of the fire, be actually obtained a determinate number, whether 3 or 4 or 5 or fewer or more, of substances worthy of differing denominations. Proposition 4, page 46. It may likewise be granted that those distinct substances which concretes generally either afford or are made up of, may without very much inconvenience be called the elements or principles of them. To paraphrase: 1. Matter is made from small particles of differing shapes and sizes and motions. 2. These particles may cluster into small lumps, and those small lumps aggregate to make macroscopic materials, and that the material might be difficult to separate out into its components. 3. Fire can be used to separate out a material into several other materials. 4. The materials that a material can be separated into are called their elements or principles. The axioms of Freind come after those of Boyle, and those of Lemery appear to have come before Boyle. Lemery, A Course on Chemistry, page 9. For example, if you mix an acid spirit with the salt of tartar or some other alkali, the edges of the acid will so insinuate into the pores of the salt that if by distillation you would separate the acid spirit again from the salt, you'll never be able to effect it. The acid will have lost almost all its strength because the edges of these spirits are so far destroyed or changed that they no longer preserve their former figure. End of quote. Lemery, A Course in Chemistry, page 22. By admitting many kinds of salts in plants, and I conceive with much more probability that the volatile alkali salt is a part of the acid essential salt I spoke of, which having been first disposed to a volatile nature and afterwards driven by the force of fire, draws along with it a portion of the empyreumatical oil that gives it such a disagreeable smell, and the same terrestrious calcined matter with which it is so strongly united, and which changes its nature, by breaking the saline points and rendering them porous, so that any acid liquor being cast upon it enters into the pores and violently divides the parts, whence follows the effervescency. For the points of the acid, which are in continual motion, entering into the pores of this salt, where there is not enough space for them to move in, and therefore they disperse themselves and break into parts with violence. End of quote. There are quite a few passages using a similar approach in said book. While I'm not aware of Lemery making a clean declaration of his atomic theory, he clearly seems to have the view that atoms have shape and that it is shape of these atoms that affect their properties. Acids have sharp edges and alkali salts have pores. In an interaction between an acid and an alkali, the edges break off in the pores, creating new atoms. Implicitly, this would require the edges themselves are entities that can, by some process, be created and attached to other atoms. Hence, the rules of Lemery would be somewhat as follows. 1. Material is made of small particles. 2. The shape of these particles causes the properties of the materials. 3. The shape of these particles can be changed by direct action on each other. 4. Acids have spikes and alkalis have pores into which the spikes fit and break off. This shows that there is a determined effort by several people to produce some collection of axioms of atomic theory. However, it really was not until quantum chemistry that this approach yielded real results, and the work had to wait until electromagnetics was put on a sound footing before moving to quantum theory. The quantum atomic hypothesis was formed in the early 20th century. Empedocles the ancient and Dirac the modern were on the same path 3,000 years apart. Dirac had the advantage of training in the results of centuries of extreme developments in mathematics. During 1963 to 64, Paul Dirac, 1902 to 1984, lectured at Yeshiva University in the Belfort Graduate School of Science. These lectures were published in 1964 by the Yeshiva University and later, 2001, in a Dover edition. In the first lecture, The Hamiltonian Method, Dirac says, "In atomic theory we have to deal with various fields. There are some fields which are very familiar, like the electromagnetic and the gravitational fields, but in recent times we have a number of other fields also to concern ourselves with, because, according to the general ideas of de Broglie and Schrödinger, every particle is associated with waves, and these waves may be considered a field. So we have in atomic physics the general problem of setting up a theory of various fields in interaction with each other. We need a theory conforming to the principles of quantum mechanics, but it is quite a difficult matter to get such a theory." End of quote. I cannot read ancient Greek. I am relying on the translation given in Fragments of Empedocles. However, since that translation is poetic and uses such forms as ere and hath, I will paraphrase even that as well, from the poem on nature dedicated to Pausanias. The four roots of all materials are called Zeus, Hera, Dis, and Nestus. These elements exist for all time and fill all space. There are no voids in any of these four. There is no creation or destruction, only a change in the mixture of these four elements making up all the material that we observe, including ourselves. Once that local mixture that is ourselves breaks apart, we cease to exist, but the material continues to exist. There are two forces in the world called love and hate. Love draws the primary elements together and binds them, while hate unbinds and separates them. This constant imbalance is the source of all the change that we see around us in the behaviour of material. End of paraphrase. The problem with this is that it comes first from a person writing about 2,500 years ago, in a different culture with different presumptions about literature and science, and in an ancient language no longer actively spoken. Even if it was spoken, the meaning of the words would have changed. And it is written as a poem, which already makes the original cryptic. Further, it has been translated over 100 years ago by someone who insists on using terms that were out of common usage hundreds of years before then to give it an artificial gloss of philosophic wisdom. And now I have paraphrased that. If you believe that the original intention is sure to have survived all that, then I have a bridge to sell you. However, I will say that it is plausible that the intention of Empedocles was rather similar to that of Dirac. Dirac had the advantage of a couple of thousand years of developments in mathematics and knowledge of modern mechanics, including relativity and electromagnetics, and information that was obtained by much sophisticated instrumentation. But I discern through a glass darkly a common thought, one that exists through the centuries of chem and alchemy, and while it took a back seat in chemistry and classical chemistry, it again rose in quantum theory. The idea of Dirac in quantum electrodynamics is that there are several fields, the photon field, the electron field, and the positron field. The electron and positron fields do not directly interact with each other, but they both interact with the photon field, causing them to wax or wane and generate the emergent effect of attraction and repulsion, which could equally have been called love and hate. Unlike Empedocles, however, Dirac formed a highly sophisticated differential equation that made it possible to describe at least one version of a semi-classical atom, electrons in a classical Coulomb potential, as electrons around the nucleus of an atom. So an analogy to Lemery, Boyle and Freind, the atomic postulates of Dirac, never written in this manner, would be: there exists a point-like nucleus of positive charge. There exists a number of electrons which do not interact with each other and are rather like vapor in nature, in that they can be more or less dense, but the total amount always remains the same. There is a quantum field around the nucleus that prescribes the possible shapes of each electron in the absence of photons. These shapes are called orbitals. At most, one electron takes up the shape of any given orbital. Electrons move between these orbitals, which have different energies as a result of interaction with photons. The shapes and motions are given in terms of solutions to a differential equation. The difference between Dirac and, for example, Freind is that Dirac gave a precise mathematical description that allows computation of detailed electrochemical properties of atoms. It predicts what elements exist and their chemical properties, although the calculations are very hard to actually carry out. But with approximations and supercomputers, this has been done.